Good evening, everybody. We'll give just a minute or two for people to get in from the waiting room before we officially start, but thanks for being here. I would ask those of you while you're logging on to make sure that your names are fully represented on your Zoom square. You remember how to change your name. Some of you we already know, and so we could change your name for you. But those of you who are new, like I see somebody with just some numbers, 538297. If you could change your Zoom name. Lauren, were you going to put something in the chat, or maybe you did how to do so?
Yep, I'm doing that right now.
Okay. To give you some instructions, but we'll get started while you do that. I think there's somebody else in the waiting room, but I'd like to welcome you all to tonight's workshop on battery energy storage for first responders. Those of you who've attended earlier sessions in the series are familiar with this introduction, so thanks for bearing with me. But there are a few new folks tonight, so I will introduce myself. I'm Nancy Bernstein. I am an energy circuit rider with ANCA, the Adirondack North Country Association. I'm also one of 2 clean energy communities coordinators for the North Country region. That is a NYSERDA program. NYSERDA is the New York State Energy Research Development Authority. And Clean Energy Communities is a NYSERDA program for encouraging municipalities to take clean energy actions. And one of those is these training series available for you. Let's see, before we get started, as I said, please take a moment to change your name on your Zoom square. This is important because we're taking attendance so that you can get credit for attending this session, and especially for those of you who are code enforcement officials, we need your correct name on your square so that we can provide it to Department of State to give you your hours. So maybe I think Lauren put it in the chat, but just to for those of you who didn't understand, you want to hover over the dots on the upper right side of your square, and you'll see these 3 dots. If you hover your mouse cursor over your square, then you'll get these 3 dots. Click on those 3 dots, and you'll see a menu of options. Rename, you click on rename, and then you get a place where you can put your full name in, so you know who you are. In addition, for those of you who are code enforcement officers, please provide your New York State training ID number. If you didn't put it in your registration when you registered, then we need that to submit. So again, you can get your in-service hours from Department of State. And this number starts with 2 letters. I'm sure you're more familiar with it than I am, but it's different than your CEO number, which doesn't have letters. And I learned that for the last session we did for code enforcement officers, that we need your training ID number. But I think that's that. Let's see, you should all be muted at this point, and we ask that you stay muted so it's quiet for Candace. And please, if you have questions during the program, to enter them into the chat or write them down so you remember them at the end. We'll have, I'm guessing that Candace will probably go through her whole presentation, and we'll have be able to answer questions at the end. So if you put them in the chat, anytime during the presentation, we'll be able to access them at the end and answer them. Let's see, another housekeeping kind of thing is I just wanted to remind everybody we'll be providing the slide deck and a recording of the webinar afterwards. NYSERDA will be sending the attendance to the Department of State for code officers to get your credit. And so you'll receive that, I know, in several weeks or so. And then for the other folks on the call, or on the call, you'll be receiving continuing education certificates from your individual counties. So you can expect that. Most of you have already gotten them for previous sessions. So I think that's it on housekeeping. I'd like to introduce tonight's presenter. You may remember Candace from our first session that we had last month on clean energy and your comprehensive plan. Candace Rossi is from NYSERDA, and she will be teaching us about battery energy storage. So turn it over to you, Candace.
All right. Well, thank you everyone for having me, and happy to be back after doing the original first presentation on the comprehensive plan. So my name is Candace Rossi, and I'm a senior project manager here at NYSERDA. And I work on NYSERDA's clean energy siting team, which if you've been on previous trainings, I'm sure you've heard a bunch about already at this point. But basically our team works with local governments across the state on any clean energy questions that you may have. We develop resources and work directly with communities across the state on issues relating to clean energy. We'll happily meet with your town or host county-wide workshops, kind of like what we're doing tonight, and really want you to take this as an introduction to our team, as we're here to help you along the way as you work through different clean energy projects or adopting laws, or really any questions you might have. We don't really anticipate you to absorb everything that we'll be talking about tonight on the first go around. So definitely want you to feel comfortable reaching out to us afterwards with any questions that you may have. And we're also consistently looking at basically what and how to develop resources to be best utilized by local governments. We don't want to just put out a fact sheet and say, here you go. We really want to provide you with the tools and templates that can be implemented on the local level to be in line with your community's character. So like I said, please take this as an introduction. And if you ask me any question I don't have an answer for tonight, I'm happy to go try to figure that out for you and provide it to you afterwards. And also, like Nancy said, feel free to put your questions in the chat. And if I notice them and can answer them quickly, I'll try to do that during the presentation. If not, we can revisit at the end. We'll have a little question and answer section, and we can discuss anything there.
Candace, would you mind could I interrupt you for a second, because I forgot something that I wanted to mention, and I wanted to introduce Cassandra Buell for just a minute, who's the Director of Planning and Community Development in Lewis County, because I had asked Cassandra to just give a short introduction, and then I totally missed it. So Cassandra just had a couple sentences to say, and that'll be a kind of a segue into why it's important to take these trainings. So from the county perspective.
Thank you, Nancy. It's Monday, so we're all in that mindset right now. So thank you everybody for joining us. We're really excited to work with ANCA to deliver this series, especially for our Lewis County code enforcement officers, our planning boards, and even our municipal officials. So the discussion for battery energy storage for first responders today, very important. From a planning perspective, it's involving our emergency management team. In the review process of solar developments is critical, especially when battery storage is involved. So while there are requirements for developers to follow with the New York State Fire Code, it's always beneficial for municipalities to also adopt the subsequent local battery energy storage laws for further protection. And that can be from ensuring that there is a staircase to access rooftop energy storage systems, to emergency shutoff information, to an emergency operations plan. A well-drafted local law for these energy storage systems is a great benefit for our first responders, and their safety is priority for us. A reminder to Lewis County participants, I know Nancy had mentioned that you'll be receiving a certificate of training completion. We just like to remind you all to reach out to us for those certificates so that you do receive credit, because sometimes it's difficult for us to match up. If there's a phone number, sometimes I don't always know. I saw Glenn is on there, Mackenzie and Tana Diana, but sometimes it's just easier if you reach out to us and let us know that you're looking for that certificate. So that's just my quick housekeeping item. And again, thank you for joining us for this.
Thank you, Cassandra. And back to you, Candace. Thanks for letting us interrupt you.
Yeah, all good. Thank you. So just following with that, so just in this course tonight, we will do an overview of what battery energy storage systems are, and then do a detailed walkthrough of the 2020 Fire Code of New York State. which is the current fire code that's enacted. And we've also pulled, as part of our energy storage guidebook, we've actually pulled out majority of the code references for energy storage. So I'm actually going to throw that into the chat in case anyone wants to follow along that way, or just weren't aware and would like it. So I'm going to put that in right now. And you can see as section 4 from that link is the 2020 New York State Uniform Fire Prevention and Building Code. And from there, it just basically has some excerpts from the code relating specifically to energy storage, just to make everybody's life a little easier. Okay, and then although this course, the title of the course say it's for first responders, it's probably more useful for code officials and all local officials to really get that baseline understanding of the amount of safety requirements these systems must abide by within the code itself. It's always beneficial, as Cassandra said earlier, is also to look at adopting a local battery energy storage law. So you're covering parts and zoning that isn't covered in the Uniform Code. Which is also on that link that I just shared in the chat as well. So this course is certified for in-service credits by the Department of State for the following 2 topic hours. And then for anyone who's looking to get Department of State credits, there are some additional course attendance rules that must be met if you're looking to receive those credits. So basically make sure if you've logged in that you don't log out during the presentation. And if you do, to make sure to log back in quickly, just because we have to make sure that you are logged in for the entirety of the course to be able to receive that credit from the Department of State. And yeah, so I'll be asking some poll questions as we go through the training today. And I will just ask that you reply your answer in the chat. That's just to make sure that you guys are paying attention. So let's get started. First, like I said, we're going to dive into an overview of energy storage systems, how they're used, different types and system designs. If you've joined some of the previous training series, some of this may be repetitive, but it's important for all of us to get onto the same baseline level of knowledge to understand the remainder of the course. So New York has some of the most ambitious clean energy goals in the country, and batteries are going to be necessary for us to meet those goals. Renewable energy is an intermittent resource, and battery storage can help make the grid more reliable. And this is really just a quick example of what the grid of the future will look like. As an example of what is happening on the slide, the renewable energy resource or the grid will basically charge the battery, which will be dispatched to the home, buildings, or for grid services. We'll get a bit more into the different applications for energy storage as we continue the presentation, but really in its most basic form, this is how energy storage is being utilized on our electric grid. Now, there are 5 overarching buckets of energy storage technology types. We have them on the screen. So there's pumped hydro, mechanical, electrochemical, thermal, and chemical or hydrogen. So pumped hydro is usually not the first thing you think about when you think about energy storage systems, but it is considered one. So this consists of pumping water into an elevated reservoir when electricity prices are low and releasing it to spin turbines and generate electricity when demand is high. And like I said, this is not necessarily what you think about when you think about energy storage, but it's an old and prevalent technology. Next, we have the mechanical storage technologies. They look to harness kinetic energy to store energy like flywheels and compressed air. So similar to hydro, but with compressed air is those compressed air systems. So instead of pumping water from a lower to an elevated pond in a compressed air system, ambient air or another gas is compressed and stored under pressure in an underground cavern or container. And basically when electricity is required, the pressurized air is heated and expanded in an expansion turbine, driving a generator for power production. Next, there's thermal energy, which is looking to capture heat, and cold to create energy on demand or offset energy needs. A facility can use off-peak electricity rates, which are lower at night, let's say to produce ice, which can then be incorporated into a building's cooling system to lower demand for energy during the day. There's also chemical or hydrogen energy storage, which basically has excess electricity generation that can be converted into hydrogen and stored. And basically hydrogen can then be stored and eventually re-electrified. And then lastly, we'll talk about what we're going to be focusing on today and what you can anticipate to see mostly in your jurisdictions, which is electrochemical batteries. So these are your lead acid, lithium ion, things of that nature. So each cell contains a positive terminal and a negative terminal, and there's an electrolyte that allows ions to move between the terminals, which allows current to flow out of the battery to perform work. Advances in technology and materials have greatly increased the reliability, output, and density of modern battery systems, and economies of scale have dramatically reduced the associated costs. So they're just, really want to highlight that there are different types of energy storage systems that are currently being utilized, but today we're really going to focus in on the electrochemical. So we'll hone in a little further on the electrochemical battery types. All of these batteries we're talking about really have three major components: the anode, the cathode, and the electrolyte. The electrolyte is just a medium to allow current to go back and forth between the anode and the cathode, or the positive and negative terminals, which is charging and discharging the battery. And then the anode, cathode, and electrolyte can be made of a wide array of different chemistries, and we'll get more into why that matters in a bit. The chemistry determines how the batteries will perform. So depending on the chemistry, they may be more efficient, more or less expensive to build and operate, larger or smaller, and be able to provide electricity for varying periods of time. So depending on the application, different battery chemistries may be preferred. You're probably familiar with lead acid batteries, as they're the most extensively used rechargeable battery technology, and they really have been the standard for decades. And then we have the lithium ion, is really what we'll be focusing on today. The first batteries were used for consumer electronics, and now, building on the success of those batteries, companies are developing and utilizing larger format cells for use in these energy storage applications. So the lithium ion batteries are, what's in your phones, laptops, and EVs, and are likely to be the most widely deployed as energy storage systems. So you can see in the chart that lithium ion tend to have a high round trip efficiency than other types. So that means less energy is lost in the storage process. The typical duration is pretty standard, as well as the time to build. The operating cost for lithium ion is low, and the cost of batteries have fallen probably by, I think, 90% in the past 3 decades, and they require limited maintenance during their lifetime. And they also have a very long cycle life. The cycle life of batteries is the number of charge and discharge cycles that the battery can complete before losing performance. So having that high cycle life is definitely a positive. So you can kind of see from the chart that these are some of the reasons why lithium ion batteries are really taking off. And this isn't shown on the chart, but different chemistries also present different safety considerations. And those concerns are typically addressed and are addressed through the New York State Code and the standards. So we have quiz question 1. So on the screen, we have, why are lithium ion batteries increasing in popularity? If everyone just wants to throw their answer into the chat, we can give you a few to think about it and see how it goes. All right, so it looks like we have a consensus, which is correct. So it's D, all the above. Lithium ion are increasing because of high energy density, declining costs, and fast dispatch time. And here pictured is a lithium ion system in Westchester County. I think this system is a little under 400 kilowatt hours and is located in a commercial area. So continuing on, we're going to basically talk more about electrochemical batteries. And this slide here is really meant to just demystify what we're talking about when we talk about batteries. So energy systems usually consist of three components. And first is the cell that is considered the building block of the energy storage system. These tend to be very small, like the size of AA batteries or something that's in your cell phone or your TV remote. And when you start stringing cells together, you get what's called the module. And then when multiple modules are wired together, that creates the battery rack. So in the end, the battery racks are really just a bunch of smaller battery cells wired together to create a larger unit. That's also why you see a lot of these energy storage systems come in different sizing, is because there is a lot of flexibility depending, when designing the system on how large of a project they need or not. The one thing also that all these systems have is the battery management system. The battery management system, or the BMS, is a technology that is dedicated to the oversight of the battery system, including monitoring the battery, providing battery protection, estimating the battery's operational state, optimizing battery performance, reporting operational status to external devices. It's basically the brains, the eyes, and the ears of the system. And it can also monitor each individual cell within the system and make sure that it's operating properly. So if there's any issue outside normal cell, module, or rack operating characteristics, it can be isolated. It can isolate the cell to avoid it from damaging additional cells. So not only is it watching and making sure everything is operating properly, it can also manage and deal with any uncharacteristic issue that occur within the system. So why are we even doing this regarding battery storage? So most people are familiar with storage as a backup system in the event of a power failure, but it also has a ton of other largely untapped potential. So energy storage can be cited at three different levels. You have behind the meter, at the distribution level, or at the transmission level. So there are different applications for each kind of grouping we have here. And this is like a pretty neat chart that I think helps provide some, visual aid to see the different ways that energy storage can be used. So the ISO or RTO services, that's on the transmission level. So I'll quickly give an overview of what each one of these applications are. So first on the chart, you have the energy arbitrage. So it's simply as purchasing wholesale electricity when the price of electricity is low and storing it, and then selling it back when the electric prices are higher. So basically selling it back during the day. So basically buy low, sell high. Next, there's the spin and non-spin reserves. So spinning reserve is a generation capacity that is online and able to serve load immediately in response to an unexpected contingency event, such as an unplanned generation outage. Non-spinning reserve is generation capacity that can respond to contingency events within a short period of time. Next, on the transmission level, this is the storage can be used for frequency regulation. So this is the immediate and automatic response of power to a change in locally sensed system frequency, either from a system or from elements of the system. So regulation is required to ensure that the system-wide generation is perfectly matched with the system level load on a moment-by-moment basis to avoid spikes or dips, which can create grid instability. So energy storage can help in that world as well. It also can support the transmission level voltage support, which ensures reliable and continuous electricity flow across the power grid. And then it also aids in what's called a black start. So in the event of a grid outage, black start generation assets are needed to restore operation to large power stations in order to bring the regional grid back online. When it comes to utility services, these generally fall into two categories. There's system upgrade deferral or resource adequacy, and then transmission congestion relief. So first on the graph, we have resource adequacy, which would mean instead of investing in new expensive generation, utilities can pay for other assets such as energy storage to incrementally defer or reduce the need for new generation. And then there's also the transmission congestion relief, and how storage can help that. Basically, storage can be deployed downstream to minimize congestion in the transmission system. And then there's the transmission and distribution deferral. Once again, this is in being able, gives the utility the flexibility to be able to delay or reduce the size or avoiding utility investments in transmission and distribution systems by relying on energy storage. And then on the customer services level, this is how storage can provide direct benefits to end users, such as you and me and more of our companies that we might work for and local businesses. So first up is the time of use bill management. So by minimizing electricity purchases during peak electricity consumption hours when time of use rates are highest, and basically can shift these purchases to periods of lower rates. So behind the meter customers can use energy storage to reduce their bill. So this is similar to energy arbitrage, but happening more on our end user level. They can help with demand charge reduction. So a lot of businesses pay demand charges on their utility bills. So this could help reduce a building's peak demand charge by shifting the time of consumption. So if they usually have large demand charges around, let's say 2 p.m. or 3 p.m., that could be a time they could, disperse or utilize the energy that they've stored to avoid those peak demand hours. Next, we have the increased PV self-consumption. So basically minimizing the export of energy generated by solar systems and maximize the financial benefit of solar. Energy storage can be used for that. And lastly, the one I think everyone thinks of is in the event of a grid failure, storage paired with local generators can also provide backup power. And here's an example of why energy storage is really taking off through the state. So across New York, peak electric demand is met in part by 50 oil and gas-fired peaker power plants and peaking units at larger plants. These facilities include both combustion turbines designed to ramp up quickly to meet peak demand and aging steam turbines now used infrequently to meet peak needs. So more than 1/3 of New York's peaker plants primarily burn oil, and 3/4 are over 30 years old, which is resulting in numerous inefficient plants with high rates of greenhouse gas and health damaging pollutant emissions for every unit of electricity that's generated. For example, on that really hot summer day and everyone has their air conditioners on, it's likely the grid is at what we would call peak demand. So peak demand is the highest level of power that the grid may be using at one time on a daily basis. So to ensure that grid does not go offline, these gas peaker plants are needed to help meet this peak demand level. And batteries now have an opportunity to provide the same service, but with greater capacity and a quicker dispatch time. So not only can batteries dispatch energy to the grid, but they can also take energy off the grid if needed as well. They're able to provide the same service, but would not need to be on such a stringent standby requirement, as batteries are able to be used for other applications at the same time, but can still be prepared to meet for peak demand events. So these older peaker plants are also paid to be on standby. So even if there's not a peak demand event, they will be paid to just be waiting for one. Energy storage also has the ability to replace these gas peakers with a much higher range of capacity. And energy storage can provide simultaneous grid services, while older peaker plants are generally slow to respond or only used for peak demand because they are expensive. And peaker plants are also typically disproportionately located in disadvantaged communities where vulnerable populations already experience high levels of health and environmental burdens. So renewable energy and energy storage systems are beginning to emerge as competitive replacements for this older fossil fuel infrastructure. So now that we've just did a bit of an introduction on what energy storage is, how it works, and why it's becoming prevalent, we're going to review what the potential battery failure sequences may be and what the corresponding diagnosis is. So when it comes to lithium-ion batteries, thermal runaway is one of the primary risks to be alerted of. Thermal runaway is a reaction in which the lithium-ion cell enters an uncontrollable self-heating state. This can result in off-gassing, high temperatures, smoke, or fire, as you can see on the screen. There is also what we're referring to as the preventive region and the containment region based on how the risk has escalated. For example, if there is some sort of battery abuse, a puncture or overheating of some sort, that could cause cell damage, and the system may begin to off-gas. This is still in the preventative region on the chart. And on the next slide, we'll go through the different protections in each region. But if this off-gassing continues, it may begin to heat release, which will cause smoking. This can translate to ignition and then to a fire, which may propagate and cause more battery abuse throughout the whole battery system. So once thermal runaway has started, it really cannot be stopped. So energy storage systems have to have a device that can recognize when the temperature is rising. And this device, which is usually the battery management system, should isolate that area and send a signal to the owner of the system that there's currently a problem. And when there is battery abuse or off-gassing, there's still time to prevent the spread of thermal runaway. But usually once smoke or fire is visible, a thermal runaway event is underway and it will need to be contained. So this slide shows the same image, but now with the thermal runaway protections that are embedded into projects and are required by the Uniform Code as well. So in the preventative region, this is where the quality of the cell or the environmental system controls may prevent thermal runaway. As we spoke about before, the battery management system will be able to detect the system is not operating correctly and may be able to isolate the issue prior to it propagating to the next cell. If there is off-gassing, the off-gas detection system and temperature monitoring should be able to give warning as well, and you can prevent the system from continuing in the thermal runaway event. Once the system starts to smoke, you're really now in containment mode as the system is in a thermal runaway event. As you can see, as the middle progresses, there are more safety measures in place to contain the event. And you'll hear more about each one of these controls as we go through the code. And just as an awareness, as everything we are going to speak about going forward is in the New York State Uniform Code, and there's no need for any local adoption as it's already required safety measures that are being embedded. Before getting into specific requirements, I think it's important to understand the applicable codes and how we got here in New York State. So in 2019, NYSERDA worked with the Department of State to adopt the 2019 Energy Storage Supplement that amended the Uniform Code at that time. This stemmed from the limited provisions that were in the current Uniform Code that were based off the 2015 International Code Council's codes. As New York State recently put out incentives for energy storage, we want to ensure that each system was built as safely as possible. We didn't want to see development happen too quickly, but safely was a real importance. So this amendment updated the energy storage fire safety requirements to the draft 2021 codes and is likely the most stringent code still in place across the country. So the Uniform Code is this law statewide outside of New York City, which has its own codes. But this supplement has been incorporated into the latest code cycle and is fully part and incorporated into the New York State Uniform Code. And so we'll start, this presentation will cover the requirements at a high level. We probably won't convey every single detail and nuance. we always, hope you refer to the Uniform Code for complete system requirements. But also, as stated earlier in the presentation, we did try to pull a lot of the energy storage excerpts out of the code and include them as part of our storage guidebook, make your life a little bit easier. So now we'll move into fire safety compliance that is required for non-residential systems, which will include most commercial and utility scale systems. So to kick off this section, we're starting with the scope of the IFC. Basically the scope of this section is relevant for all battery energy storage systems having capacities that exceed the value shown in this table. So really any lithium ion battery exceeding 20 kilowatt hours must comply with this section. If the system is in a group R3 or R4 occupancy, they shall comply with section 1206.18. But basically the purpose of this is showing that any battery over 20 kilowatt hours will have to, any lithium ion battery over 20 kilowatt hours will have to meet all the requirements we're about to set forth. So here are all the construction documents that are required to be submitted along with the permit application required by the Uniform Code. So we will go through the code in more in depth and more in detail on many of these requirements and how they'll be met. But when basically an applicant provides their permit, they need to make sure they include the location and layout diagram, details on the fire resistance rating of assemblies, the quantities and types of battery energy storage, any manufacturer specs, ratings, and listings, the description of the battery management system, the location and content of the required signage. And while there is signage required in this fire code, there's also signage that's required as part of the National Electric Code on the electric side, which we won't cover today, but just something else to be aware of. They'll have to provide the details on fire suppression and detection, thermal management, ventilation, exhaust, and venting systems, which we'll get more in depth as we go through the presentation. The support arrangement for installation, and then the commissioning and decommissioning plans, and if required, the peer reviewer identification and qualifications. So here we have the requirement for the hazard mitigation analysis. So this is only required for energy storage technologies that were not listed in that initial scope. When there's more than one technology that is provided in a room or enclosed area, or where allowed as a basis for increasing the maximum allowable quantities. So we'll get to the maximum allowable quantities in a few slides, but really what that is stating is that any lithium ion system over 600 kilowatt hours will be required to perform this analysis. And if you're familiar with our battery storage guidebook, this is also where we've gotten the threshold to basically differentiate between tier 1 and tier 2 systems. Is that anything over 600 kilowatt hours would be tier 2, and they would also have to go through this hazard mitigation analysis. So this study is done to evaluate the consequences of different failure modes. These are usually done by an engineering firm for the town to determine the best approach on how to handle a failure. The analysis will evaluate the consequences of the following failure modes. So you have the thermal runaway in a single rack or module or unit, failure of any battery management system, what's going to happen, what happens if there's failure of a ventilation system, what if there's a voltage surge on the primary electric supply, what if there's short circuits on the load side of the storage system, what if there's a failure of the smoke, fire, gas detection or fire suppression, or the failure of a spill neutralization or containment system. And then the local fire code may approve this analysis, provided that the consequences of the analysis demonstrate that fires will be contained for the minimum duration of the fire resistance and detected in time to allow occupants to safely evacuate. This could also be approved that they show that toxic and highly toxic gases released during fires will not reach concentrations in excess of immediately dangerous to the life or health level in the building or adjacent means of egress routes during the time necessary to evacuate from the area. And it also has to show that flammable gases will not exceed 25% of their lower flammability limit and will be controlled through ventilation of the gases, preventing accumulation. So really, this is the test and analysis right out the gate that these projects will have to basically evaluate these consequences if there is this sort of failure, and then also explain to the fire code official and show to them that, you know, these are the levels, like I said, like the fires will be contained for this minimum duration. So, and then next we have the large scale fire test. So this is where required. Large scale fire testing must be conducted on a representative energy storage system in accordance with UL 9540A or an approved equivalent by an approved testing laboratory. So the test must show that a fire involving one system will not propagate to an adjacent system. So most of the design requirements for energy storage is to ensure that if there is an incident or fire, that it does not spread to neighboring cell, module, or racks. This also needs to show that if a fire does occur, it will be contained within the area for the duration of the fire resistance rating of the room assemblies. And also the test report must be provided to the fire code official for review and approval. There's also a few requirements throughout the code that can be altered based on the results of large scale fire testing. And that's something I'll highlight as we go through the presentation. So making sure everyone's still awake, we have quiz question 2. So what is large scale fire testing not supposed to demonstrate? And if you just want to put your answers in the chat. All right, it seems we have a consensus with A, and you are correct. Large-scale fire testing is not supposed to demonstrate that a system will never catch fire, but rather to show that the fire will be contained as necessary. And this is also a 20 megawatt system that was installed in Stillwater, New York, just to give you kind of an idea of what these look like throughout the state. So here we have the fire remediation requirement. So where a fire or another event has damaged the energy storage system, the owner of the system has to, at their own expense, immediately dispatch one or more fire mitigation personnel to the premises and remain on duty continuously, even after the local fire department leaves, and basically have to stay there until the damaged system is removed, or earlier if the public safety hazard has been abated. So this requirement was really put in place to alleviate the fire service of potentially babysitting an energy storage system after a fire or if an emergency took place. There's possibility that energy storage system may reignite after extinguishment, and the owner is responsible for the safety of these systems. So basically they have to contract a fire remediation company that will be called to the scene to relieve the fire department and then start the decommissioning process. And I'll just really highlight that this is at the expense of the system owner. Here we have the peer review requirement that's in the code, which I think is a bit unique. So where required by the town, the system owner is responsible for retaining and furnishing the services of a registered design professional or special expert who will perform as a peer reviewer. And the cost of these special services will be borne by the system owner. So basically, and I think understandably, a lot of the information that we're going to go through tonight might be a bit complex, especially if you're looking at it in an application package. So no one, basically the code is not expecting anyone to be an expert overnight on this. So this gives the opportunity for a town, if they don't feel like they have the required information or knowledge to fully review one of these application packages, that basically the energy storage system owner is required to furnish you with a peer reviewer. So basically this, they're required to provide you with a design professional, but if the design professional is not really the scope of the work for the questions that you're asking, an approved special expert may be employed by the owner. It's also important to note that the special expert can't just be the applicant's brother and decide to pretend that he knows what he's talking about. They do need to provide basically documentation submitted to the fire code official for review and approval that they do have the skill set that is necessary for the questions that are being asked by the town. So I think this is just interesting to keep in mind when you are reviewing, if you do get applications coming in, if they're commercial and over that 20 kilowatt hours, there is the requirement here for peer review assistance. So yeah, I think that's unique and definitely something you should keep in mind. So here we have the commissioning plan requirements that are necessary via the code. So commissioning needs to take place to ensure that the system will perform as intended and is required to occur prior to the project being placed into service. So specifically, the commissioning plan itself needs to provide and include a narrative of the description of the activities that will be accomplished during each phase of commissioning, including the personnel that's intended to accomplish each of the activities. You need to provide a listing of the specific energy storage system and components, controls, and safety related devices to be tested, and a description of the test to be performed and functions to be tested. Need to provide the conditions under which all testing will be performed, documentation of the owner's project requirements and basis of design necessary to understand the installation and operation of the system, verification that the required equipment and systems are installed in accordance with the approved plan. You need to provide the integrated testing for all fire and safety systems. You need to provide the testing for any required thermal management, ventilation, or exhaust systems associated with the energy storage installation. Need to provide the preparation, delivery of the operation and maintenance documentation, which we'll discuss on the next slide. Need to provide, as part of the plan, the training of facility operating and maintenance staff. You need to give the identification and documentation of the requirements for maintaining system performance to meet the original design intent, and the identification and documentation of personnel who are qualified to service, maintain, and decommission the system, and also respond to incidents involving the system. So this is the section of the commissioning plan where they need to lay out who that fire remediation team is that will be responding. And then last, it also requires you to provide a decommissioning plan, which we'll discuss in upcoming slides as well. And basically all of this needs to be approved by the fire code official prior to the start of commissioning. And then it also requires a commissioning report that describes the results of the commissioning to be provided to the code official before the final inspection and approval. So there is a lot of information up front that the applicants are required to provide to the town to show that their project is installed safely and has met all these requirements prior to going to operation. And here is the operation and maintenance manual requirement. So this must be provided to both the system owner and to the system operator before the energy storage system is put into operation. The energy storage system must be operated and maintained in accordance with this manual, and a copy of the manual must be retained on site. So the operation maintenance manual must clearly identify the required routine maintenance actions, include the contact information of the agency that is contracted to service the system, needs to provide the maintenance and calibration information, including wiring diagrams, control diagrams, system programming instructions. It needs to outline desired control set points. It needs to provide a schedule for inspecting and recalibrating all controls. Also needs to have a service record log, and then basically have all that inspection and testing records that need to be maintained in this manual. And here we have the decommissioning plan requirements. So this needs to be submitted as part of the commissioning plan. The town must be notified prior to system decommissioning that it's occurring. The plan includes details on providing a safe and orderly shutdown of the system, and must include a narrative of the activities to be accomplished for removing the system from service and from the facility in which it is located. and also needs a listing of any contingencies for removing an intact operational system from service and for removing a system that has been damaged by a fire or an event. We will not really be getting into the details of how to manage an incident if there is one, but we do have on our website a posted webinar on incident management that one of our contractors assisted us with when we held our energy storage webinar series, not this past summer, but the summer before, which I'll throw a link in the chat to that as well, but I'll also provide to Nancy when I give her my slides so she can share in case you don't get the link tonight. All right, so I just threw that in the chat if anyone wanted to look at it. And next we have the equipment listing that's requirement. So to further safeguard against hazards, systems must also be listed in accordance with UL 9540, the standard for energy storage systems and equipment. So chargers, inverters, energy storage management systems, if not covered as part of that UL 9540 listing, it must be listed separately. And this is basically just giving all those different listings that are required for parts of the system. So here we have the battery storage, the battery energy storage management system requirement. So as I've stated a few times tonight, this is considered an instrumental safety feature of the energy storage system, and is considered the eyes and the ears of the battery system's health. The device is constantly monitoring the state of health of the system. If the battery management system were to fail, that would definitely lose a major safety feature. And this is probably the most important feature of the system in its effort to prevent thermal runaway, as it's able to detect anything that's abnormal and able to isolate those cells or modules. So where required by the energy storage system listing, an approved energy storage management system that monitors and balances cell voltages, currents, and temperatures within the manufacturer's specification. The system shall also disconnect any electrical connections to the energy storage system or otherwise place it in a safe condition if potential hazardous temperatures or other conditions such as short circuits or over voltage or under voltage are detected. So here we have the enclosures. So all energy storage enclosures should be made of non-combustible material, and this is to contain the fire within the enclosure, if there is one, so that the heat does not transfer to other enclosures. So now we're moving into what's called the general installation requirements of the code, and we'll be beginning with the electrical disconnect. So basically, once again, all systems that this code is relevant to must meet all these general installation requirements. So for electrical disconnects, these are extremely important, largely to first responders, and they should be in a secure location with signage to direct the fire department to the proper place. Even though you may shut down the energy storage system, the stored energy inside the batteries does not just dissipate. So that is a key point to be aware of. This one device can shut down all cabinet or containers that are at the site. So firefighters should be advised to be careful when shutting down the system when there are no signs of fire. When there is a problem within the section of the system, the battery management system will generally isolate that particular section and stop it from charging and discharging. But in the event of a fire, the fire department should seek advice before shutting down the full system at the location. If there's no person to advise the fire department and there's clear signs of fire, then the incident commander should shut down the system before any type of fire tactics are being used. So we have the working requirement, working clearance requirement here. So basically the access and working space shall be provided and maintained about all electrical equipment to permit ready and safe operation and maintenance of such equipment. And the manufacturers, in accordance with NFP 70 and the manufacturer's instructions, the clearance for working equipment should be 3 feet according to NFP 70, and these clearances should always be unobstructed. And fire departments may go out to do a site visit if they want to notify the owner of the equipment when they're not in compliance of the regulations. So they can always check that out. Here we have the fire resistant rated construction requirement. So rooms and other indoor areas containing energy storage systems should be separated from other areas of the buildings. They shall have a 2-hour minimum fire rating for all installations. The fire protection should also include the ceiling of the room that they're in, but this is not required for walk-in containers. Also for indoor areas, energy storage systems shall be permitted to be in the same room as the equipment they support. I think this requirement is pretty obvious why, but you definitely want to ensure if there's an incident concerning fire that there's high enough fire rating for the building to be evacuated to protect human health. So moving along here, we have the seismic and structural design requirements. This is pretty standard. The installation will have to comply with the seismic design requirements in Chapter 16 of the International Building Code and shall not exceed the floor loading limitation. Once again, I think the need for this is pretty obvious. Next, we have the vehicle impact protection. So when an energy storage system may be subject to impact by a motor vehicle, including forklifts, you need to provide some sort of vehicle impact protection. So this is always, impact is always a concern, and it should prevent a vehicle from driving into the system. A vehicle that plows into these batteries can cause serious failure of that system and can become a major challenge for firefighters as well. I don't think anyone wants to drive a forklift or a new car into an energy storage system. That definitely won't be fun for anyone. And this is just taking from an actual installation that we visited in Brooklyn. So pretty standard vehicle impact protection, as you've seen around other installations, not just energy storage. Once again, I think a pretty common sense requirement, combustible materials should not be located within 3 feet of cabinets containing energy storage systems or within a walk-in unit or room. Having a fire on the exterior of the system could possibly cause the batteries to fail and lead to a fire in the energy storage system. So usually best to avoid any potential fires close to an energy storage system. The next general requirement we have here is for toxic and highly toxic gases. So systems that are installed indoors and have the potential to release toxic and highly toxic gas during normal use will be required to have a hazardous exhaust system. Some batteries may release toxic gases during normal charging and discharging, and a forced fan system can be used in battery charging rooms and other areas where gases can build up in a contained space. I will note that lithium ion does not release any toxic gases during normal operation, and therefore it's not required for them to have this ventilation. Although as we get to the later slides in the presentation regarding thermal runaway protections, you will see that many lithium ion batteries will install exhaust systems similar to this. It's just to meet other requirements in the code, not this one particularly. So these are usually like lead acid batteries can release toxic gas during operation, so they're always required to have ventilation. And here we have the signage that's required for each battery energy storage system that should be provided on all entry doors to storage systems rooms, to walk-in units located outdoors, on rooftops or open parking garages, and on the enclosure of cabinets. So this is really necessary to let people know that there are batteries in this location, what type of batteries, that there is electrical, that it is energized, and what the emergency contact information is in case of an incident. There may be additional signs, like I said, that are required from the electric code, but this is specifically what is required in the fire code. You definitely don't want random people walking into rooms with these systems in there. And if there is an incident, you want to be aware of what you're walking into. Also, while there are different electrochemical types of batteries, and we saw in earlier slides, they're not all created equal. It's also of how you would respond to them could be different based on that electrochemical. So you really want to know what type of battery is in a room if there is an incident. And this is the wrong quiz question, so I think you guys get a quiz question number 3 because didn't make it in. Got a double, but that's all right. So here we are still in the general installation requirements, and this is the security of installations requirement. You want to ensure that the systems are secured against unauthorized entry and safeguarded in an approved manner. Security barriers, fences, landscaping, and other enclosures should be used to inhibit any required airflow or exhaust from the system. And also the energy storage system has a lot of stored energy that could injure people when they come in contact with the system. So you really just want to make sure that these systems, especially if they're outside, have the fence around them, and if they are in rooms or indoors, that they're secured from any unauthorized entry. Next, we have requirements for systems that are located in occupied work centers. You need to ensure that they are locked in non-combustible cabinets or enclosures to prevent unauthorized access. Additionally, they must be placed within 10 feet of the equipment that they support. So basically, if you're installing energy storage indoors at a school and office building, you just want to make sure they're locked in non-combustible cabinets or enclosures and located if they're supporting specific equipment. So here we have the open rack installation requirement. So where systems are installed in a separate equipment room and only authorized personnel have access to that room, they shall be permitted to be installed on an open rack. This is a common theme that these systems are secure from unauthorized access, as they can pose hazards. You really want to make sure that only authorized personnel have access to the room. And I think the open rack requirement here is much more common to lead acid batteries than it is lithium ion. So usually you'll only see this when it comes to lead acid batteries. And then our last general installation requirement here. So these units are defined as an enclosure that is not for human occupancy, but can be entered for only maintenance, replacement, repairs, and inspections. So for walk-in units, the risk of these containers presenting a life hazard inside during the event is significantly less than with systems located indoors, especially when compared to non-dedicated use buildings. Unless there really is a reason to believe someone is inside, you really should stay out. These containers are likely what you'll be seeing frequently throughout the state as storage becomes more prevalent. But once again, you really shouldn't be having your lunch in a walk-in container and should only be accessed for a real need of the system. So we just went through everything that was considered our general installation requirements that all systems within that scope must meet unless there is a specific exemption listed in the code. So now we'll start going through the beginning of the electrochemical storage system protection requirements. So here we have the size and separation requirement. So grouping of energy storage systems to a maximum of 50 kilowatt hours is there to reduce the fire load of a group or a rack. This grouping does not apply to remote outdoor installations, which I think is important to flag. It does, however, apply to walk-in containers or cabinets that are outdoor and near other exposures. So walk-in units that are near exposures, while they need to have spacing between groups, they don't need spacing between a group and the wall of the walk-in unit. This also applies to energy storage systems that are in rooms or areas that are indoors. There are two exceptions to this requirement. One is for communication utilities, and the other one is based on large-scale fire testing. So as we spoke about earlier, there is one requirement that based on large-scale fire testing, that there will not be propagation of fire or any other hazards. This requirement can be changed per the fire code official, and often for walk-in units, smaller separation distances are allowed based on the results of those large-scale fire testing. So I think this is probably the most frequent exemption that you'll see in the code is regarding to the size and separation. So this slide represents, hold on. So this slide represents the maximum allowable quantities that were discussed earlier in the presentation. If an installer wants to exceed the values in this table, they will need to conduct the hazard mitigation analysis and large-scale fire testing to show that the system will be safe. There are two other exceptions, lead acid or nickel batteries under the control of communication utilities again, and dedicated use buildings. Also of note, you can see that lithium ion systems exceeding 600 kilowatt hours will need to go through the additional testing. So if you are familiar with NYSERDA's model battery energy storage system law, this is a reasoning defining systems into those two tiers, over and under 600 kilowatt hours, with projects over 600 kilowatt hours having many more requirements to meet than those that are under 600. And also, if you'll give me 1 second, it seems that I copied question 2 into this presentation multiple times for some reason. So I'm going to stop sharing for a second and just fix that.
Suppose this is a good time for folks to run to the bathroom or go get a drink of water or something like that. Well, Candace.
Yeah, should be another minute or so.
Yeah.
Probably quicker. Here we go. Let's see how fast this updates
That
here.
was fast.
All right. Well, now I have question 4. While everyone's answering question 4, I can make sure the rest of the questions are correct. So just if everyone wants to answer in the chat for any lithium ion batteries exceeding 600 kilowatt hours, the hazard mitigation analysis and large scale fire testing are both required, true or false? All right, looks like we have a consensus for true, and you guys are correct. And it looks like the rest of my questions should be correct. So we'll just keep on moving on. Sorry about that. So here we have the requirement for mixed electrochemical systems. So this is a requirement if there are mixed electrochemical systems in a single area. So you'll see this when people use a different battery chemistry that are typically used for critical operating protection systems, such as like alarms, HVAC, smoke, purge ventilation. So these critical components should always work when the energy storage is completely shut down by first responders or the battery management system. So basically a lot of times for these outdoor larger systems, you'll see that they have like a control room kind of on site sometimes. And within that site, they'll sometimes have lead acid batteries there. So basically this is just a formula that the code has put in place to ensure that this total percentage does not exceed it. And if so, I think you need to go through large scale fire testing. But even so, when you have those backup lead acid systems, if they're in a separate room, that wouldn't be the same room as the lithium ion as it would be outside. But just something to keep in mind that there is this specific formula that needs to be met for these systems. So here we have the elevation requirement. So the International Fire Code has used this language for many sections within the fire code. The system cannot be located higher than 75 feet above the lowest level of fire department vehicle access or on floors located below the lowest level of exit discharge. So there are exceptions for each of these systems if approved by the fire code official. So they can be permitted to be on higher or lower floors. based on that additional hazard mitigation analysis or the large scale fire testing. And they can also be permitted in underground vaults if approved by the fire code official. And there are specific batteries, lead acid or nickel, for the communication utilities again, that don't have to meet these thresholds. So basically the fire department officials do have a right to permit higher, but only if they feel comfortable with the energy storage safety features and the fire protection systems that are involved. And if they don't need to approve this one. So when systems are inside a controlled room or enclosure, the smoke alarm is generally the easiest way to sense a fire. So basically some installations use certain technology that is constantly checking the air for any type of abnormal component. So you also have the IR radiant systems that check for heat. If there's temperature rise, it will send a signal to the alarm panel that will notify the fire department that there's a problem. So you have these central stations that are used to monitor fire alarms and make notifications to the fire department that a location is sending a signal from a smoke detector or a radiant heat detector. So here we have the fire suppression system requirement. This is necessary as a containment response to any thermal runaway or any issues in the system. So these systems can be set up as a sprinkler water system or a clean agent based system. So there is the automatic sprinkler system that requires a minimum water density or whatever is determined based on large scale fire testing. So although the code calls out this water density, sometimes there may be a challenge to get that much water density if there's, a really tall building and that's where the system is installed, or even in an area that doesn't have good water pressure. So in outdoor locations, some towns are using a dry pipe that the fire department pumper is supplying the water. And this is used so that the automatic water suppression system do not accidentally freeze or malfunction and cause the water to flow in a system that had no problems. But this would be kind of a conversation between the applicant and the town on what's going to be utilized. And then they also have alternative automatic fire extinguishing systems listed here if approved by the fire code official, and also has to be based on large scale fire testing. So a little bit more visual to the fire suppression systems. This is from a project that's located downstate. So this container specifically had two separate types of suppression. It has the water fire suppression. So you can see basically that they have a fusible link that will allow water to flow, and basically the lead fusible link is melted out from the heat. So these suppression systems should not be open head sprinkler or spray nozzles, and the water should only be placed on these systems when there's a known fire event. So basically for this water sprinkler system, it gets too hot, this glass thing basically breaks, and then they're able to supply water to the system. And then they also have clean agent or gas systems set up next to it as well. You can kind of notice the difference between the two nozzle assemblies. So depending on what is happening inside the container, they have two different fire suppression methodologies that they can utilize. And this is from that same project. So I had mentioned very quickly that you could utilize a dry standpipe into these walk-in containers. That can be included as part of the fire suppression system design. So the standpipe is a type of rigid water piping, which is built into the energy storage unit, to which fire hoses can be connected, allowing manual application of water to the fire. The pipe is in place permanently when an intake, usually located near a road or a driveway, so that the fire engine can supply water to the system. The standpipe supply pipe extends into the container to supply firefighting water to the interior of the structure via those hose outlets. And dry standpipes are not filled with water until needed. So firefighters often are the ones bringing in the hoses and attaching them to these outlets to basically flood the inside of the container. This is not always possible for every installation, as you might not have the water supply that's able to utilize that, but it's definitely something to consider. So here we have the maximum enclosure size. So the code does set forth a size limitation for each one of these containers. So these currently have volume limitations. So as the energy density continues to get smaller and smaller, responders should definitely be aware that there could be a lot of energy that's being stored in these containers. I think it's interesting that the original supplement back in 2019 had the requirement being the dimensions that are listed on the screen. But when it was open to public comment and adopted into the Uniform Code, it was basically opted to do a volume requirement instead. So that's where you get that volumetric 4,028 cubic feet, which also equates those dimensions. So here for the vegetation control, so any areas within 10 feet of an energy storage system must be clear of all vegetation except ground cover vegetation like grass. This I think is pretty obvious as well. It's required to prevent a fire spreading to different locations outside the enclosure if there is a fire outside the enclosure. But once again, you are allowed to reduce this clearance to combustible vegetation based on your large scale fire testing. So that once again would be totally up to the fire code official, but I think we're mostly seeing projects really sticking with that 10 feet. And next we have the means of egress separation. So basically this one really focuses on ones for storage systems that are in a parking garage or outdoors. So egress from an open parking garage is very important, and these systems should not be within 10 feet of those pathways. Once again, code officials can approve smaller distances based on that large scale fire testing, but a continuous and clear path from any occupied portion of a building to a public way, such as an outdoor sidewalk, must be provided. And a means of egress consists of three parts: the exit access, the exit, and the exit discharge. So basically the path within the building that leads to an exit, the doors to the outside, and the route from the exit to the public way. So this is also an requirement in the code. So we really just covered all the requirements for commercial systems. Majority of these requirements are put in place to prevent a thermal runaway event. But now we're going to talk about the different requirements necessary for different battery technologies. So kind of like I said before, not all batteries are created equal, and different chemistries can lead to different compliance that is required to maintain safety. So this table is showing the battery technology type, the chemistry, and is giving a glance of some of the protections that are needed for specific chemistry types. So there's different requirements based on the chemistry. And like I highlighted before, we're really seeing majority of lithium ion batteries coming into New York at this point. But you can see from the 5 different requirements, lithium ion only has to meet 2 of them: explosion control and thermal runaway. And we'll discuss a bit more why that is as we go through the slides. So I guess I'll highlight one more thing on this table, is that you can see for lead acid that all 5 of these requirements are required, and similar with nickel. And then they're basically lithium ion is really the only one that only has 2 out of the 5. One of the reasons why for like spill control is that lithium ion doesn't have a liquid electrolyte like lead acid does, so it's not at risk of spill. And we'll continue going through. I'll try to highlight the differences between the battery techs as we do that. So the first requirement here is for exhaust ventilation. So this is required for rooms, areas, and walk-in energy storage units that contain certain electrochemistries. This is not required for lithium ion, but for all other battery types, such as lead acid batteries are capable of releasing hydrogen gas due to overcharging or other events. So this ventilation requirement is really focused on that. The developer will need to install a ventilation fan for walk-in units with battery chemistries other than lithium ion. The ventilation needs to be designed to limit the maximum concentration of flammable gas to 25% of the lower flammability limit. or provide continuous ventilation. And there also needs to be standby power for at least 2 hours, and it needs to be supervised by a remote station. So this is just kind of highlighting this requirement for standby power. This could when you see multiple types of electrochemistries in a room. And also it may be required for lithium ion as a method of explosion control, which we'll discuss in a few slides. It may be required for the responder to remove flammable gas due to a thermal runaway event, and they just can turn on the switch, which should be remote from the system. And also they have signage, which should direct responders to the ventilation fan and how to utilize it. So once again, this is not a requirement for lithium ion, but you'll likely see these installed in lithium ion projects for another requirement, which is explosion control. So as part of the exhaust ventilation requirement, a gas detection system is required to monitor the levels of gas in the unit. And this will trigger appropriate ventilation and inform operators of unusual levels of off-gassing. And any failure of the gas detection systems will also trigger a trouble signal. So some energy storage chemistries have a liquid corrosive electrolyte. And these corrosives can burn skin and damage first responders' PPE. So the responders should follow their department's standard operating procedures when responding to any corrosive spills regarding energy storage. So basically this is required. Lead acid is an example of batteries with a liquid electrolyte. So they have to make sure that they have this specific spill control and neutralization implemented on site for those projects. So here is the explosion control requirement that is necessary for all battery types. So this is kind of when you see lithium ion utilizing exhaust ventilation. So explosion control can really be handled in 2 separate ways. We have the deflagration venting, which utilizes pressure panels. And then if there's enough built up gas pressure in the unit, it will push open the panels and release the gas. So most lithium ion systems will have deflagration venting panels that will manage the overpressure or blast wave that is produced in an explosion if there is one. That blast wave will be sent through the venting panels and should maintain the integrity of the container. And these panels venting direction should be directed to an area that will not interfere with the fire department's operation. And then you have the deflagration prevention, which can be done using exhaust fans and limiting the lower flammability limit to 25%. And once again, this is the requirement that you will see having applicants putting exhaust fans and ventilation in their lithium ion systems. So next requirement is the safety caps. So basically vented batteries and other energy storage shall be provided with flame arresting safety caps. So hydrogen is a byproduct of lead acid battery charging and discharging process. So rooms or containers that have these systems should have a ventilation fan inside that will turn on when flammable gases in each room reaches 25% of the lower flammability limit. In regards to valve regulated lead acid batteries, the gas is captured and then releases when the pressure on the safety caps reach a point that is considered overpressurized, and the caps will open and release the gas buildup. So once again, this is not a requirement for lithium ion. And then next we have the thermal runaway, which is something that we had talked about earlier. And once it starts, it cannot be stopped. So energy storage systems should have a device that can recognize when that temperature is rising, and the device should isolate that area and send a signal to the owner of the system that a problem exists. That device is the battery management system. So also data has shown that stopping the charging and discharging of a cell is an effective measure to prevent a cell from going into thermal runaway. So on the right of the screen, it shows the stages of what a thermal runaway event can look like. A method must be in place to prevent the cell from going into thermal runaway and prevent the spread to adjacent cells. So you have that overcharge, maybe heat or piercing in step 1. Step 2, that one cell is going, affecting the cells next to it. And then 3, it's continuing to propagate a bit. And in this image, it shows that 4, they're putting water on those specific cells. That could just be the battery management system instead of putting water specifically on those cells, as that's a bit difficult. Could just be isolating that entire module from the rest of the system to ensure that it doesn't propagate. All right, so quiz question 5. Do all electrochemical battery energy storage types require the same fire safety requirements? If you want to just put your answer in the chat. All right, and with the consensus of B, you guys are correct again. So the answer is no. Many safety requirements vary based on the hazards associated with different chemistries. All right, so to review, we've now gone over the requirements that all commercial and utility installations will need to meet, as well as additional requirements based on systems chemistry. So now lastly, we'll go over the different requirements needed based on where the system is located. So this is something that was cool in the 2021 draft codes that we adopted in New York State. Is, the 2015 codes really just looked at battery storage as kind of the same thing. The 2018 code looked at, not all batteries are created equal. There's different requirements for different electrochemicals. And in the 2021 code, they took it a step further that, it's not just the type of battery, but also where the battery is located could have different safety requirements. Basically, if it's going to be close to humans' health or, remotely placed. So yeah, now we'll go over those different requirements. So this is just a quick overview slide of some of the different locations we're going to talk about and how the requirements differ. So first we have the dedicated use building. So these are only used for the purpose of housing an energy storage system or any grid related operations. Only admin personnel can be within the building, but the area that can be used is limited to 10% of the floor space. And then, so obviously this is like a system this is a building only for energy storage, really nothing else. And then here is another example of what an extremely large dedicated use building may look like. And then the other type of indoor installations are what's called a non-dedicated use buildings. So some examples of this could be colleges, work centers, residential apartment buildings. And this slide is just showing pictures of a few systems installed in mixed use buildings. So here is a chart that's provided in the code, which is a list of all the compliance that indoor installations need to meet. So we have already reviewed the general installations requirement, the electrochemical protections, the chemistry specific protection. And you can see here now when we're looking at where the project is located, that the maximum allowable quantities is not required for dedicated use buildings. So if you have a building that's only meant to be energy storage, you're not going to have that cap of 600 kilowatt hours. Especially as there's not an immediate threat to human health. So some requirements are allowed to be waived. And then there's 2 additional requirements that are needed for indoor installations that we'll review in a slide or 2. But first, we're going to have another quiz question. So for indoor installations, which of the following is not required for both dedicated use and non-dedicated use buildings? All right, we got some answers in, but not the one I was hoping to see. So we have the answer here is C. So dedicated use buildings may exceed the maximum allowable quantities requirement. So both of those dedicated and non-dedicated use buildings still need to meet the size and separation, the smoke and automatic fire detection and fire resistant rated separations. But for dedicated use buildings, they do not need to follow the maximum allowable quantities requirement. So continuing on, the next two slides are two requirements that are only for indoor installations. The first one is called the dwelling units and sleeping units, and this is basically stating that energy storage cannot be installed inside a dwelling location. So if an energy storage system fails, it could release some sort of toxic fume that could overcome a human pretty quickly. So we really don't recommend putting these into your bedroom or anywhere else where people may be living. They should be separated in their own area. No one's usually sleeping next to their boiler either. You don't necessarily want to sleep next to an energy storage system. And next is there's an additional fire resistance rated separation requirement for indoor installations. So 2-hour fire barriers are needed in a room or area for indoor installations. And horizontal assemblies refers to the ceilings as well as the walls. So for dedicated use buildings, you need to have this 2-hour fire barrier separate from that admin and support personnel that's allowed to take up 10% of that building. And for non-dedicated use buildings, they need to be, this 2-hour fire barrier need to be separate from other building areas. So now moving on to outdoor installations. Outdoor installations are really defined as either being remote or near exposures. So a system's considered remote by the code if it's at least 100 feet clearance from buildings, lot lines, public ways, stored combustible materials, and really anything else that might be hazardous. And installations near exposures is literally defined as not remote, as we describe above. So basically anything within 100 feet of buildings, lot lines, or public ways is considered near exposure. So once again, we have this chart that's provided in the code. So remote systems may not have the same requirements as other outdoor systems. These remote systems will not have the same life safety risk factor involved. So their requirements may be a little less stringent in some areas. You can note in the subscript on the suppression system that we have for remote installations that were approved by the fire code official, fire suppression systems are permitted to be omitted. Once again, that'll be a conversation between the applicant and the fire code official to make sure there's a plan in place. So they can allow for that suppression system be removed. We would always recommend some sort of battery suppression system to be available to control a potential fire inside of walk-in containers when the fire department responders cannot get water inside the container. But regardless of the fire department well-intentioned to extinguish the fire, fire departments can take defensive posture in this case and not allow basically the fire to spread to other containers and basically just contain it if there is a fire. Again, for remote installations, size and separation is not required. And maximum allowable quantity section, once again, is not required, but it is for all other systems for the installations near exposures. And once again, we have one new requirement that we'll be discussing. But first, we'll have another quiz question. So for outdoor installations, which safety requirements are not applicable if the installation is considered remote? All right, I'm seeing an abundance of D's, which is correct. Both size and separation and max allowable quantities are not required for remote outdoor installations. So here is just an example of some larger walk-in containers or cabinet systems. You can see there's the maximum allowable, the maximum enclosure size. It's also important to note that the HVAC units and exhaust ventilation is not included in the maximum enclosure size. So that's why those are not included as being above there. You can also see how it has the security of installation, so how it's being secured from outside access. And there's also the immediate means of egress for these outdoor systems. As I mentioned before, they have the HVAC units and exhaust ventilation. So these have those ventilation systems involved in case there is some sort of off-gassing that needs to be controlled. So this is just another image of what these walk-in containers look like from a different aspect. So you can kind of see, if you really wanted to, you can kind of walk down the middle of them, and usually the energy storage is along the wall. They have the battery rack there. They have a fire suppression system. The energy management system is on the outside, the HVAC, battery control panel, and power inverter. So once again, just kind of giving you another idea of what these look like. And here, this is an example of some of the energy storage cabinets that house batteries that can be installed outside. And here's just another one as well, an outdoor cabinet system. This can also show you how size and separation compliance isn't required when the system is considered remote. And then for outdoor installations, we have requirements to talk through that's only required for them. So basically they have a specific clearance to exposure requirement. So for all projects, they need to be at least 10 feet from lot lines, public ways, buildings, and really anything. And that's used as a fire barrier. This distance can be reduced by either large scale fire testing or placing a fire barrier between the storage system and the structure. The fire barrier should be at least 1 hour fire rated. The second option is for the building that is adjacent to energy storage to make sure it's non-combustible and has a 2 hour fire rating with no openings or combustible overhangs. And then for any systems that are installed on exterior walls, they can be installed outside, but they need to meet the requirements that are represented on the slide. So the max capacity of each unit needs to be under 20 kilowatt hours. They need to be installed according to the manufacturer's specs. They have individual unit separation and need to be, 5 feet from doors, windows, or any buildings, openings to buildings. But once again, you can have smaller separation for 4 and 5 based on the large scale fire testing for this project. So the code also spells out 2 additional locations, which they call special battery energy storage installations. So these are for projects that are installed on rooftops or open parking garages. So they have a similar of the requirements of the indoor and outdoor systems, that they need to meet the general installation requirements, size separation. They have to meet that, as well as maximum allowable quantities. But they have some additional requirements that are specific to rooftops and open parking garage installations. So we'll talk through those. So both of these special installations have to meet this requirement for clearance to exposures. So once again, they have to be 10 feet from everything that's listing on the slide. So buildings, lot lines, public ways. And then there's also exceptions that would allow the distance to be reduced to 3 feet if they meet those requirements. So if they have that 1 hour barrier 5 feet above and around the system boundary, or if they have non-combustible weatherproof enclosure around the system, and large scale fire testing demonstrates that if there is a fire, it would not spread, they could have a reduced distance. So there's also a specific fire suppression requirement that both types of projects need to meet. And they have to have the automatic fire suppression system inside enclosures of walk-in units, but battery energy storage systems on parking levels that are not open to the sky. So basically, as long as you're not on the top level, you need to have this requirement. But once again, it could be exempt if large-scale fire testing demonstrates that fire will not impact exposures in the open parking garage. So these are just specific requirements for rooftop installations. Some of them are pretty obvious, that emergency personnel they must have access to the roof via a stairwell. That service walkways from the access point to system are at least 5 feet in width. Basically, you want to make sure the system is not located on the edge of the roof for obvious reasons. You could have that standpipe that we talked about installed at a roof location, and also the system has to be at least 10 feet from fire service access points on the roof. So basically, for systems on the roof, you're really making sure that the system is installed safely and with enough room to give firefighters decent access if there is some sort of issue. Both rooftops and open parking garages have to be at least 50 feet from building HVAC inlets. And then here we have for open parking garages, the system cannot be located within 25 feet of exits where located on a covered level. And then you need to have a fence with a locked gate or another approved barrier to keep general public at least 5 feet from the outer enclosure of the system. So that was a very quick and wordy way to go through the requirements for commercial and utility size systems in the fire code. I definitely recommend you give, our section of the energy storage guidebook a further look to see, but wanted to make sure you guys all had a quick, not even quick, a decent overview and introduction to all the safety compliance that's required via the Uniform Code. And I'll have my contact information on the last slide, and also have Nancy send it out, that if you guys have any questions going further in depth into this, I'm also happy to be a resource. And now we're just going to review some of the requirements for residential systems in the residential code and what protections are in place to avoid any incidents. So here are just 2 images to give you context of what a residential system might look like. Majority of these are pre-packaged. So the residential threshold sizes shown here are from the 2020 residential code and are subject to the uniform requirements, the limitations of which are imposed on to ensure the safety of systems. So each individual unit may not exceed 20 kilowatt hours, which is, we'll talk a little bit more on the other side, but when you're looking at systems as a whole, the system as a whole cannot exceed basically 40 kilowatt hours within utility closets or storage or utility spaces. So basically, if it had its own little boiler room, you could still only be at 40 kilowatt hours. But if you have the system in an attached or detached garage or accessory structure on the exterior walls of your house or outdoors on the ground, you can have a system that's up to 80 kilowatt hours. And if you go over those requirements, you go over that size threshold, there's a more in-depth requirements that these systems need to meet, even if they are installed on residential property. So here, individual units have a maximum rating of 20 kilowatt hours, and individual units shall be separated from each other by a minimum of 3 feet, and individual units installed outdoors on exterior walls shall be located at least 3 feet from doors and windows. An average residential unit is usually around 12 to 16 kilowatt hours. And you can also notice the installations we have on the screen. The one with the X through it is wrong because you cannot install energy storage within living spaces as much as some companies would want us to. And no matter how cool they look, they definitely should not be installed within living areas. And the other one is in the garage, is installed properly, but may still require other features that are not in the picture. So for indoor residential systems, There is a specific fire resistant rating that must be met. So rooms that contain energy storage systems have to be protected by fire resistance rating of 5/8 inch type X gypsum board or equivalent installed on walls and ceilings. For attached garages, they have to be protected on the system size by fire resistant construction, which I believe for R302 is basically a 1 hour tested 1 hour resistance from exposures on both sides. And basically to ensure that if there is an incident, the walls can resist spreading the fire. If there is an issue, and you'll have enough time to evacuate. Next is the fire detection requirement. So you have to have smoke alarms installed in the area where the energy storage is installed. And if smoke alarms can't be installed, a heat alarm should be installed and connected to your smoke alarm system. So if you have a system that's located outside, it might be difficult to utilize a smoke detector. So a lot of those are using a heat detector system instead to recognize a temperature increase inside the system. And lastly, we have the ventilation requirement. So indoor installations of energy storage that include batteries that produce hydrogen or other flammable gases during charging, such as lead acid, you might have to meet the exhaust ventilation requirements of the code. So usually these fans will turn on when gases reach 25% of the lower flammability limit of the room, and these ventilation fans will also be needed when a toxic gas is produced during normal charging or discharging of the storage system. And once again, unlike the conventional lead acid batteries, which produce hydrogen gas, the individual cells in lithium ion do not require ventilation as they do not release toxic gas during normal operations. And lastly, we have quiz question number 8. A single family homeowner wants to install a battery energy storage system in their garage with a capacity exceeding 30 kilowatt hours. Should it be installed in accordance with section R327 of the New York State Residential Code or section 1206 of the New York State Fire Code? And we seem to have a consensus of Bs, which is correct. If you exceed that threshold, there is a specific section in the fire code in 1206 that you will need to go through. And that is all I have for you guys tonight. So I'm happy to take any questions if you might have. And then I'll also make sure to send Nancy my slides as well as my contact information and some of the links I shared tonight, so you also have access to that. But thanks for having me. I'm happy to take any questions that you might have.
Thanks very much, Candace. Folks have any questions? I'm not sure I saw any in the chat. There's been so much, answers to all the questions that sometimes it's hard to miss any. But if anybody has any questions, please, you can put that in there now, or we're a small enough group that it'd be fine to unmute and ask verbally. I found that really interesting, Candace. That was a lot of information, and I never would have known there was that much to know about the safety of batteries. But we're going to see more and more of them in the future, and so making sure they're installed safely is critical.
Yeah, I think New York State might still have some of the most stringent codes. Like we're on the 2021 when the rest of our codes are actually on like the 2018 draft. Like the emergency adoption put us on that 2021. So everyone else, all the other states that utilize the ICC codes like New York State does, they're probably mostly still on the 2018 codes, which we are for the rest of our building code for the most part that I'm aware of at least. But that basically that emergency ruling and adoption had to skip forward a code cycle or two to make sure that these projects are installed safely and with the best information at hand, instead of waiting probably. I don't think next code cycle is still like a year away, so we wouldn't be on those codes yet, and they're already drafting 2024. So we'll see how those move along. If we continue on the path we are, with just making sure these projects are installed safety with as much, safety measures as necessary.
Yeah. Appreciate that. Any questions for Candace? Maybe everybody's just digesting all that we heard. And if you do, I'll when I send out the recording and the slide deck, we'll have Candace's information in the slide deck, but I'll also put it in the email. So if you ever have questions, I'm sure she won't mind being contacted and giving out good answers. But if there isn't any questions to be had, then I'll just thank everybody. This is the last training in this series, and thanks to everyone who attended. We hope you found the subject matter helpful for continuing the work that you do in your communities. To those of you who are code officials, we hope to host another 8-hour in-person workshop on energy code enforcement training. And we've had a few in the past, and we hope to have another one maybe in the spring, and I'll be sending out information to folks when we have a date and location. Otherwise, for more specific information on battery storage trainings, I know Candace put a link in the chat, and maybe is that, I don't know if that's one of them, but I'll put that the link to trainings that you can, there are recorded trainings that you can check out if you feel the need to learn more. I'll put that in the email that I send out. But thanks everybody for attending. Thank you, Candace, for presenting, and I hope everybody has a wonderful holiday season.
All right, thank you. Everyone have a good one.
All right, bye-bye.